decision in energy market. And if we have an idealized market where the market optimization problem can be modeled with a convex optimization problem, then we can just directly get electricity prices as the shadow prices of this convex optimization, and those type of prices has all the nice type of properties. However, in reality, the energy market is far from idealized. We could have discrete decisions in the day-ahead market, such as turning on generators decisions and on and off statuses. And we could also have nonlinear structures such as AC power flow, and those complicate the pricing problem. Our solution to this challenge is to derive convexification of the mixed integer optimization problems that represent the energy market optimization and derive pricing schemes from this convexification. There are two parts of this work. In the first part, I will talk about my recent paper that's accepted as appeared in Management Science. That's about copositive duality for discrete energy market. For the second part, I'll talk about an ongoing work that extended our previous energy management science papers that uses semi-definite programming relaxation for pricing in markets with both discrete decisions and nonlinear structure. So here's an overview of part one of this work. In this part, we derive a copositive programming duality framework to deal with pricing problems and also gain problems with discrete decisions.
So, do you have any material on like how do markets deal with these non-convexities?
How do I what?
How do the markets deal with these non-convexities when they, because they solve the market day by day, hour by hour, right? So how do they deal with them?
That's a good question. That's in the literature review.
Okay, good.
Practitioners usually solve like a mixed integer program to do that. It's not ideal, but yeah, I'll get to that.
Okay, good.
So an overview of our part one, we start from a mixed integer linear program, which is non-convex, and we'll reformulate this non-convex problem to a convex counterpart using completely positive program. Using this reformulation, we can provide a notion of duality for discrete problems using copositive duality. And here's a flowchart of what we do. We start from a non-convex problem. We reformulate it with a completely positive program, which is convex. And completely positive program has strong duality, and its dual is called copositive program. We use this framework first to derive pricing schemes in energy markets. And since copositive programs are NP-hard and there is no existing commercial solver can solve it, we also propose a novel exact cutting plan algorithm to solve copositive programs. We also use this framework to deal with games with discrete decisions. And this isn't in our paper, but I still want to mention this. We deal with discrete games and derive theoretical results and computational results for discrete games. And I believe this framework is very useful for many types of economic problems with discrete decisions because convex optimization and duality theory are kind of ubiquitous in economic analysis. So first, let's look at the unique commitment problem that I deal with. It's a non-convex type of energy market problem. So in the day-ahead market, in practice, practitioners solve this unique commitment problem. It's a non-convex problem, and it's used to decide the schedule of generators at each hour. And here's a picture showing the result of a unique commitment problem. So unique commitment problem can be mathematically formulated as a mixed integer linear program as follows. In the objective, we are minimizing the total cost. We have demand coupling constraints that clears the market, the total supply equal to the total demand. We also have a couple of operational constraints like for capacity, etc., and they are like decoupled by generators and time. We do have binary decisions for on and off statuses and for turning on the generators. So to get our pricing scheme, we use this very fundamental mathematical result from this classical paper by Sam Bureau, 2009, published on math programming, which says that for any mixed integer linear programs on the left-hand side, which is non-convex, we can reformulate it exactly as a convex completely positive program. So how does this happen? So with this non-convex problem, we have the binary restriction. If we remove the binary restriction, then we will have a linear program, which is convex. However, we want to reinforce this relaxation. what we can do is that we can reinforce it by this single constraint. It's a rank 1 constraint that says for any binary decision, 0 equal to 0 squared, 1 equal to 1 squared. However, if we just impose this constraint, it will become a nonlinear problem because this constraint is nonlinear. So a classical method of what people do is that we just lift this quadratic term using a big X matrix, and then enforce this constraint by sk equal to big XKK. So it's kind of a linear constraint that relaxes this quadratic constraint. And then we can further reinforce this relaxation by some astral valid inequalities. There are different ways to do that. One way is to impose this reformulation linearization technique constraint as follows. So how do we get this? We can get this by multiplying the linear constraint AIX equal to BI. We can multiply the left-hand side with itself, right-hand side with itself, and get X transpose XI equal to BI squared. And then we can again lift this quadratic term using a big X matrix, and then we will get this RLT constraint. So this is a classical way of reinforcing the quadratic constraint here. There are different types of RLT constraints. This is just one type. There are other types, but this one type is enough for our purpose. Additionally, we can impose this completely positive conjugate constraint. And with all those reinforcements for the relaxation, Sam proved that this completely positive program is an exact reformulation of the non-convex problem. Also, in recent literature, it is proved that if the physical region of the original non-convex problem is bounded, then we do have strong duality for our convex program, which is very important for our pricing purposes. Okay, any questions about the math background? Okay, so now let's switch gears and talk about energy market. As many of you may know, in the energy market, the suppliers are the power plants and the demand side are the utilities. We are talking about wholesale energy market here. And then there is a system operator that acts as a platform and match the demand side with the supply side using auctions. Currently in the US, we have a two-stage wholesale market. In the day-ahead market, which happens one day before the demand happens, we solve a unique commitment problem, which is non-convex and is a missing linear program. In the spot market, which is exactly the day of the demand, the time demand happens, we have a linear program which doesn't have any discrete decisions. So this spot market problem is actually this idealized market that I mentioned. It doesn't have any non-convexity. And we can actually use the shadow price of the demand constraint of this linear program for spot market as our market equilibrium price. And this price has some very nice properties. It supports market equilibrium, and it makes sense because if you think about what the shadow price means, if we increase the demand here, we will need to use more expensive technologies, and then the shadow price will naturally increase. So more demand, higher price, which makes sense. And more formally, this price actually supports individual rationality. On a high level, individual rationality just means the outcome of the decentralized problem coincides with the outcome of the centralized problem under our price. Mathematically, individual rationality is defined as follows. If we fix the price for the profit maximization problem of the generator, then the outcome of the profit maximization problem should be the same as the outcome of the centralized system operators problem. If we can prove that, then we will have individual rationality. How do we prove this?
So if you go back one slide, your spot market is so you have index T there, so it's still like across multiple time periods, or is it affecting the?
Yeah, it's across time period. And then you get one shadow price per time period.
Okay, but you're assuming no, it's all convex. So no.
Yeah,
no
it's a linear. It's
decisions
Ethiopia,
at this
basically.
Okay.
Yes.
Although you can, of course, start and stop units on relatively short.
Yes, of course.
Basis, right?
Yeah. Just put it simply.
Sure.
So here, so X prime, the big X prime, what isn't it? What is the?
Oh, this is just a set. for different types of constraints, like ramping constraints, capacity constraints.
Okay.
Yeah, it's not the lifted. Sorry for the overlapping of the notation. So just a set. Yeah.
This is convex for now, right?
Yeah, it's convex. It's linear.
Yeah,
So
it's
very
linear,
simple.
exactly.
And then how do we prove this? We can prove this very simply. We can just do a. So we can just Lagrangeify the demand constraint. If we Lagrangeify the demand constraint, we will get the following Lagrangified linear program. And if we remove the constant term from the objective, we will end up actually with a decomposable problem. And it's decomposable by generators, and each component of this decomposable problem is actually a profit maximization problem. So in this way, we prove that the profit maximization's optimal solution coincide with the original centralized problem's optimal solution. And on a high level, this result is just like saying this lambda price acts like an invisible hand that matches demand with supply and align their incentives. This invisible hand result is nice, but it doesn't naturally extend to non-convex market because in general, we do not have shallow prices for non-convex problems like missing linear programs. There are a huge literature trying to deal with this problem. So first, this very famous paper by Richard O'Neill and co-authors that's actually used in our real life in the US. Propose a restricted pricing, which basically fix the binary decisions to their optimal level, and you end up with a linear program, and we get prices from that. That's what people do in practice right now. But the problem is that there are a lot of like uplift payments for subsidizing the generators to make them profitable. And alternatively, people have proposed this convex Hall pricing, and a modified version of the convex Hall pricing called extended locational marginal pricing is used in some of the system operators in the US. And more generally, our paper is related to the literature on pricing for divisible goods. For example, there is literature on using discrete convexity to get prices for divisible goods. And also this work by Milgram and Watt proposed an alpha pricing mechanism for individual goods. It's still an open question, what's the best way to do pricing in this field? And our proposal is to use a completely plotted program for pricing. Yes.
Can you briefly explain the difference between convex Hall pricing and ELMPs?
ELMPs?
The extended
Yes,
locational
that's a good question. From my understanding is that convex Hall pricing gets the price from the like Lagrangified demand constraint, and if you have the dual weight of this Lagrangified problem, then that will be your price. And extended locational marginal price is like simplified that idea. You don't need to solve a Lagrangified problem. Instead, you solve a very tight linear program. That's really like much easier to solve. And it's kind of an approximation of the Lagrangified problem.
But they like keep the same binary variables for all the generators.
Yeah, of course.
Okay. Like they're not, because I've seen literature where they're like, we just only assume certain generators are part of the convex Hall, and then we just relax the other ones. But that's not extended.
Probably there are proposals about that. I'm actually not sure what's exactly happening at MISO, which is using extended locational pricing.
Yeah.
I think there are papers explaining that. But like to simplify the difference, it's just like Lagrangified problem, a very tight linear program.
Okay.
That's the difference. Yeah. Any other questions? Yes.
Does that discomposition that you explained in previous one holds if you consider network constraints?
That's a very good question. So if we have network constraint, we will have some extra payment for the transmission lines. The proof still goes through, but you will have extra payment. Yeah, I think there are literature or textbooks explaining that. It's kind of classical result in like linear program. Yeah. Question. Any other questions? Okay, so yeah, so our proposal is to use a completely plotted program to get prices. As a recap, we're dealing with this non-convex unique Millen problem. And a formulation of this non-convex problem is a completely positive program that looks like this. And this problem has strong duality. The dual problem is a copositive program, which is NP-hard. And we propose we'll use all the dual variables. The shadow prices appear in the dual problem as our price. So more concretely, we propose at each time period t, the system operator will collect the following value from the demand side and pay the generator the following payment. And again, with this pricing scheme, we want to prove individual rationality, but it's not easy to extend the previous proof. But let's just try to extend the idea from the idealized market and see where the bottleneck is. So again, we dualize those demand constraints, and we also dualize the RLT, the lifted version of the demand constraint. And here's a bottleneck. We want to decompose this again by generators, but we cannot do so because of this coupling conic constraint. It's not very decomposable. So how do we deal with this? Our first idea is to make this conic constraint decomposable by some type of matrix completion theory, like in SPP, but it's kind of a dead end. It's not working. Our second idea is to make this term disappear and just to fix big lambda t to 0. And if we do this, we can prove that this Lagrangian-fied conic program is equivalent to a Lagrangian-fied mixed integer linear program, which is decomposable by generators. And in this way, we prove individual rationality for our pricing scheme. But then a natural question is, when can we get rid of this big lambda t? So we get some sufficient conditions. So basically, if big lambda t equal to 0, it means those lifted constraints are actually redundant. But in general, we don't have redundant lifted constraint. However, if we just remove those RLT constraints, even if they are not redundant, and get a modified version of our convex optimization, we can still say something about the prices we get from this modified completely positive program. So this theorem we derived says that if we have more generators than the number of time periods plus 1, then the prices we get from this modified completely positive program can guarantee that we have individual rationality for at least G minus T minus 1 generators. And the total subsidy for covering those T plus 1 generators that's not individually rational is bounded by big O T plus 1 times T.
So when you say subsidy, you mean, is that equivalent to uplift payments then?
That's a good question. So there are different types of uplift payments and subsidies. One is make-whole payment, another is loss of opportunity cost. Like here, we're talking about loss of opportunity cost. Yeah. So that's bounded by this bound. But I think make-whole payment will be lower because if you make sure individual rationality, you should have make-whole. So the make-whole should also be bounded by this. So the proof here, for the bound on the number of generators that's not individually rational, we can just use sharply for my lemma. I mean, the derivation is still a bit complicated, but on high level, we just use sharply for my lemma. To prove the bound on the subsidy, we can just use the fact that the number of non-individual rational generators are bounded by T plus 1, and also we have T time periods where we don't have binary solution, and we need to run up and run down to get the binary decisions, and multiply those together, we'll just get that bound. So this theorem on high level tells us that on a large scale system where we have more generators, much more generators than the time periods, then this subsidy is negligible. So this is a nice result. Yes.
Go back to the optimization problem. So the form of non-convexity you have here is basically just the binary decisions, right?
Which one? This one?
So what is I guess the non-convexity in this problem is just the on and off decisions, right?
And also start up decisions.
And also what?
Starting up generator. We have a startup cost, so we did.
Binaries.
Binaries, yeah, only
Right,
binaries.
right. Only binary, right? Yeah. Makes sense, yeah.
Yeah. Okay.
Meaning you're not considering like AC power
Right.
flows, is that what you're
No, we don't. But second part we have.
Yeah, so I
this
guess,
is a DC problem.
so for the cost functions of these generators, you assume that basically they're just a startup and then the rest is linear, right?
Startup, yes. Like sometimes we also include a fixed cost. I don't think that will affect the result too much. Like startup fixed cost plus linear marginal cost. Yeah, so different ways. Also, sometimes people have like quadratic cost. That also happens, or piecewise linear cost. Okay, so that's a nice result we got for the bound on subsidy. Some other nice analytical results we got include that for the system operators, the total revenue will cover the total payment, so revenue balancedness. And for the generators, the total revenue will equal to the total cost, so revenue neutrality for generators. And also for the revenue neutrality result, it's on an aggregated level, not individual level, to ensure individual revenue neutrality or revenue adequacy. We also provide a modified version of our copositive duality pricing scheme called revenue adequate copositive dual pricing that ensures individual revenue adequacy for all the generators. And the theoretical result for our original pricing scheme also extended to this setting. Sorry. We also did some experiments to verify our result. So we did experiment on this classical scarcity example. We see that the traditional restricted pricing is very volatile and requires generator-dependent prices, and also convex-conjugate pricing doesn't really ensure revenue adequacy. In contrast, our revenue adequate copositive pricing requires no uplift payment. Then let's get into the computation part. So to get our prices, we need to solve this NP hard. Yes.
Cheng, but so you're saying in your scheme there is no uplift payment, but does it mean that each generator receives a different price?
That's a good question. I don't think so. It's a uniform price in this RCDP pricing scheme. Yeah, but we do have sufficient conditions. If the sufficient conditions are not satisfied, maybe. So basically, we really need to make sure the pricing problem is feasible. It's not guaranteed. It's not always. It's always feasible. In our experiment, it is. It's an open question. Right? Yeah. Okay. So to get the prices, we need to solve this NP-hard copositive program. What people usually do is that they do a SDP approximation of this copositive program. Basically, the Colli-Con can be inner approximated with the Minkowski sum of the positive semi-definite con and the non-negative matrix con. However, this is an approximation of the problem. And in this work, we developed an exact solution method using cutting plans algorithm. So what we did was we removed this complicating Colli constraint, and to reinforce the relaxation, because we end up with a linear program now, we solve this separation problem, and this separation problem separates the copositive matrices from non-copositive matrices. And if this separation problem has a positive value, optimal value, then we add the following cutting plan to the relaxed problem, and so on and so forth, until the algorithm converges and the separation problem has a near zero objective value. The drawback here is that this algorithm converges very slowly. So that's why we also propose an enhancement of our algorithm where we tighten the master problem with some second-order constraints. And some comments on the performance of our cutting plan algorithm. First, our algorithm is really straightforward to implement. We only need to use Groby to solve the master problem and the separation problem. In contrast, there is only one non-exact copositive programming algorithm in the literature by simplicity partition, which is not that straightforward to implement. Let's just skip this. Also, we observe significant speed up with the second order con enhancement idea. But still, if we want to solve the problem exactly, we can only solve instances up to like 2 generators and 4 hours. And if we can do it approximately, we can solve instances up to 4 generators and 24 hours. It's still not very tractable in terms of power system scale. That's why in part 2 of our work, we are proposing to use an SDP relaxation of the completely positive program and provide performance guarantees on how well the prices will go if we use this relaxation. But that's part 2 of the work, of this talk. But before going to part 2, I still want to briefly mention how we can use our copositive duality framework for discrete games. It's not in our paper. It's not in the final version of our paper. It's in one of the preprint, but I want to mention it here because I think it's relevant. So we are dealing with this type of discrete games where we have discrete decisions. For example, in this prisoner's dilemma, it's an example of biometrics game. The players have binary decisions on whether to confess. Also, the Kuno game in energy market is also a type of discrete game with discrete decisions. And in general, we're dealing with games with discrete decisions where each player is solving a discrete mixed binary quadratic program as follows. We have quadratic terms in the objective and some binary variables in the constraint. So again, we use the same idea. We formulate this non-convex problem to convex completely positive program. And in this way, we kind of reformulate a discrete game to a convex game. And we can show that the Nash equilibrium of the discrete game is equivalent to the Nash equilibrium of its counterpart. So using this reformulation and equivalence result, we can extend some very classical results from convex game to the non-convex case. For example, there's this classical result about the existence of pure strategy Nash equilibrium in convex games, right? If we have those three conditions satisfied, then there exists at least one pure strategy Nash equilibrium point. And then we can extend that result to our discrete case, and we find that if our convex reformulation of the game satisfies those three conditions, then the previous conditions about Nash equilibrium existence will be true, and we do have pure strategy Nash equilibrium. In addition, if we have the following result on Slater's condition and on the payoff functions to be diagonally strictly convex, then the Nash equilibrium will also be unique. So we extended many of the classical results from the convex game to our non-convex setting, and this is novel to the literature. In addition, we can use our method, reformulation method, to compute the Nash equilibrium. So basically, we can just formulate the Crash-Kontaka KT conditions to obtain the Nash equilibrium. However, if we want to solve the KT conditions directly, then we will get some nonlinear terms in the optimization problem, and we also have some conic constraint, which is hard to solve. But we find that in a special case, if we only have discrete variables and we have all constraints being equivalent, for example, a bimetric scheme is such a special case, then we can turn the KKT conditions to a single mixed integer copositive program, and then solve the problem exactly using our cutting plan algorithm. And we tested this idea on some bimetric schemes. For those small instances we tested, they converge very fast and converges to the correct result. Of course, the state-of-the-art biometrics algorithms are faster because they are more specialized, but our method is more general and can deal with different types of discrete games. Okay, so that's part one. Any questions? Yes.
What was the rationale behind reformulating the problem as a game?
That's a good question. So put it this way, for our unique commitment problem, it's not a game because we have inelastic demand. So the decentralized solution is the same as a centralized solution. But if we have elastic demand, then we will have a game problem, a Kuno game. So we are not dealing with it right now in practice, but in the future, if we want to consider more elastic demand, then we will end up with a game. Yeah. Question.
So I guess in terms of the comparison with the existing baselines, you showed the scarps example. I guess you compare with some of the classical methods. Did you compare with, I guess, how does this compare with, let's say, our equilibrium constraint pricing?
That's a good question. We didn't really do that experiment. Let me find that result, sorry.
Yeah.
Somewhere here, yeah. We only compare with restricted pricing and conventional pricing because they are kind of used in the practice. We didn't compare with more method. So are you talking about the method you proposed in your review paper for OR?
Right. Yeah. I guess. Yeah. The equilibrium constraint pricing. Yeah. That's what. I guess. I know you refer to that paper in here, but I was wondering. I guess how does this compare with that? Given that, I guess there's a similar example, Scarf's example.
Yes, we took that example from your paper.
Okay. So then, but you didn't compare with that method.
I guess the rationale is that, like, because there are so many methods. If you're a reviewer, you might ask, I guess, but the reviewer didn't ask.
I guess you said you took the example from the paper, but you didn't compare with the method.
Yeah, we compared with the ones used in practice, and we at that time we feel like if we compare with all methods, it would be more like a review paper instead of a methodological paper. But yeah, I remember that method. I think one obstacle is that it's a bit hard to implement, if I remember correctly. You solve a nonlinear
Maybe we can
problem.
talk more
Yeah,
offline.
maybe we can talk more offline. But yeah, that's a good question. Okay, so that's a part one of this work. Any questions about part one before I jump to part two? Okay, the part two. First, I apologize for being very technical in the part two. So we get a lot of like theoretical result about SDP in part two. So it's a little bit different in flavor in part one. It's a bit like heavy. So apologize for that. But let me know if you have questions. So the part two of this work is an extension of our previous work on copositive program. So the goal of this work is to make our pricing scheme more scalable because copositive program is not that scalable, but SDP is much more scalable than copositive program. Then we want to obtain scalable pricing scheme for both DC unit commitment and also AC unit commitment, which is new to our extension with guarantees. Using SDP relaxation. The question we answered in this work is that if we approximate the completely positive program using semidefinite program, can we still derive pricing schemes with some performance guarantees on incentive deviation? And the SDP relaxation we get is as follows. It looks very similar to the previous completely positive program reformulation. The only difference is that we relax the completely positive, the NP-hard conic constraint with the positive semi-definite constraint and non-activity constraint. So this is a relaxation of the mixed integer program instead of exact reformulation. And our contributions in this extension work include a theoretical part and an application part. In the theoretical part, we really want to use this SDP approximation as a device for scientific analysis of non-convex problems, like for non-convex mixed integer linear programs and also mixed integer nonlinear programs. To do this, we derive some theoretical results about the SDP relaxation, such as strong duality and envelope theorem, and how differentiable this relaxed value function is. On the application side, we use the theoretical result and use those results to propose an SDP-based pricing scheme for both DC unit commitment problem and unit commitment problem with AC power flows. So in this result, we can deal with both discrete decisions and nonlinear structure. We also derive a tight bound on this type of subsidy called loss opportunity cost, LOC. And we find that this subsidy is bounded by the gap of the relaxation. Okay, so first let's look at this parameterized mixed integer linear program. So it's just a mixed integer linear program with right-hand side variables being parameters. So we just assume the demand in the unit commitment problem to be parameters. We also want to assume that all the variables are bounded, which is a very realistic assumption in practical problems. So we reformulate this non-convex problem to a SDP relaxation. And again, the SDP relaxation has bounded feasible region. With this assumption, we can show that SDP relaxation has strong duality. This isn't an obvious result because not every bounded SDP has strong duality. And our result is conditional on the SDP, the relaxation of the mixed integer linear program. So to prove this, we just need to show, we can just homogenize the SDP relaxation and show that its feasible region is bounded and consists of two cones and one hyperplane, and thus we have strong duality. With this strong duality result, we can extend the classical envelope theorem to our SDP setting. So the envelope theorem basically says that how the optimal objective value will change with the parameter change. And it's a sensitivity analysis result for optimization problems, and it's helpful because envelope theorem basically tells us the marginal value of demand, which we use as a price in this work. So formally, the envelope theorem says that if we have optimal dual prices from the SDP, and if the value function of SDP is differentiable, and then the derivative of this value function of SDP can be obtained as the partial derivative of the dual SDP problem's objective value. To prove this, we just use the classical envelope theorem from Milgram and Segal, which assume there are fixed feasible regions. Admittedly, we do not have a fixed feasible region because of right-hand side parameters. However, the dual SDP problem has fixed feasible regions, and because we have strong duality, we can apply this envelope theorem on the dual SDP problem. That's why we get the derivative from the dual objective of the SDP. And with this envelope theorem, we can just directly get the price as the derivative of the value function for the SDP. So basically, instead of using all the shadow prices from the Copositive program as before, we simplify our pricing scheme and just use the SDP approximation and only the sensitivity of the demand parameter as our price. So the price for the DC unit minimum problem is as follows. We just get the derivative from the value function of the SDP relaxation and use it as our price. And if we want to do that, we want to make sure that this value function is actually differentiable. And how often is it differentiable? We answer this question by showing this proposition that says that this value function is differentiable everywhere except at finally many points. How do we prove this? We prove this by showing the SDP relaxation feasible region is semi-algebraic because it consists of a spectrahedron, a cone, and a polyhedron. Because the feasible region is semi-algebraic, the value function is also semi-algebraic, and we can use the monotonicity lemma for semi-algebraic functions to show there are fairly many breakpoints for the value function, so there are fairly many non-differentiable points. So this is very helpful for our pricing. And we just use the same idea for pricing in AC unit commitment problem. The AC unit commitment problem has gained a lot of interest recently. It's not currently used in the practice, but it gained a lot of interest from both practitioners and academia recently because the AC optimal power flow problem becomes more tractable because of the DOE Go competition. However, the pricing for AC unit commitment problem is still a very much open field, and it's relatively unexplored compared with the pricing for DC unit commitment problem. There are two sources of non-convexity for AC unit commitment problem. One source is the AC power flow, and we convexify the nonlinear AC power flow constraint using the classical rectangular SDP relaxation. Basically, just lift the non-convex quadratic term for voltage to a like big W matrix. And to deal with the binary variables, we use the same idea for the DC unit commitment problem. We just do SDP relaxation for the binary variables. And again, strong duality hold and a lot of results we've seen before hold for our AC UC problem. And we can derive the prices for AC unit commitment problem by taking derivatives of the AC unit commitment problem value function in terms of both the real power demand and the reactive power demand. So we get prices for real power and also reactive power for ACUC. Okay. Then intuitively, because we get a SDP relaxation, we want to know if we have a tighter relaxation, does it give us anything good? But intuitively, if we have a tight relaxation, we should have lower subsidies, right? And we want to formalize this result. To formalize this result, we show that the subsidy called loss opportunity cost has a tight bound. So the loss opportunity cost is defined as follows. Given the prices, the loss opportunity cost is a difference between the maximum possible profit and the realized profit on the feasible solution. And this metric measures the incentive deviation under our positive price. We can show that if we have this value function for the relaxed problem, and if the prices are the subgradient of the value function for the relaxed problem, then the total loss opportunity cost is bounded by the optimality gap of this relaxed unit commitment problem. The proof uses some properties of convex conjugate, such as order reversing and the Fairchild's inequality. And our result is general. It not only applies to SDP relaxation of unit commitment problem, it also applies to other relaxations, such as Lagrangian relaxation for convex Hall pricing. One ongoing work we are working on right now is to find the sufficient conditions for the SDP-based price to be subgradient of this value function. It's not always true, so we need to find some sufficient conditions to ensure this bounding is correct. Okay, and then a natural question is whether this bound is tight. What if it's a very loose bound? So one trivial case where this bound is tight is when the relaxation is exact. So we just have a zero gap in the right-hand side, so zero LOC. A less trivial case is when we have no network congestion and if the convex conjugate of the optimal problem's value function equal to the convex conjugate of the relaxed problem's value function. And this corresponds to a special case of convex Hall pricing. If we do convex Hall pricing and if we have DC-UC problem without network constraints, then we actually have a tight bound. So this inequality becomes equality. And if any of you are familiar with the convex Hall pricing literature, this special case actually recovers a classical result about convex Hall pricing in Critic and Corsers that shows the equivalence of the loss opportunity cost and the optimality gap. So our result generalizes that classical result. We did some experiments with some Julia-based data sets, like from unit commitment package and from power models package, and we solve the SDPs with MOSAIC. We find that the SDP relaxations are often tight and it's much more scalable compared with computer programs. We can solve up to 57 buses and 24 hours, even without any enhancement. This is just using MOSAIC directly. If we use some enhancement, like in the literature, people have used the matrix completion and some like parallelization method, I think we can be even more scalable here. And also we get some preliminary result for DC-UC pricing and find that the lost opportunity cost we find that the loss opportunity cost under SDP-based pricing is 46% lower than under the restricted pricing. As a summary, in this two-part talk, in the first part, we derive a copositive duality framework for both discrete games and discrete pricing. We propose a notion of duality for discrete problems, and we provide a pricing scheme for discrete energy market problems, show good properties for that. We propose a novel cutting plan algorithm to solve the copositive programs exactly, and we also obtain theoretical and computational results for mixed binary quadratic games. In the second part, we derive theoretical results about the SDP relaxation for mixed integer and nonlinear programs, and we obtain SDP-based pricing for both DC and AC unique commitment problems that can deal with both discrete decisions and nonlinear structures. And we also obtain a tight upper bound for loss opportunity cost in terms of relaxation gap. While I'm here, I'm also excited to talk with you about the other different types of work I have done that's very different from the talk today. I have a recent work that's published, accepted at EC that derives a networked Kuno competition with coupling constraint, and we obtain insight about entry and the tariffs using that framework. And I also have this work from DOE UpRE project that deals with uncertainties in unit commitment. That's all. Thank you. Any questions?
In your talk briefly about some computational results towards the end there. Just to clarify, so you compared to here restricted pricing. So could you just remind me what is restricted pricing?
Just this pricing scheme by Richard O'Neill. Fix the binary.
Fix the binaries and then solve it as okay.
Yeah.
As a linear
As a linear program. Okay.
Yeah.
And I mean, I see unit
Yeah, we're still working on it.
commitment. I mean, that's a tough problem to solve. So,
Yeah.
like the computational side here, you're saying you can scale up to 57
Yes.
buses, but this, these systems are big, though. Do you see like potential here to use this for ISOs, RTOs in practice?
That's a good question. So in terms of pricing, I believe some ISOs use a smaller scale grid than compared with operations. For example, in New York ISO, they use a 12-zone system. So if we have a 12-zone system and don't have a lot of generators, I think it might be practical. Otherwise, I think it's more like an opportunity here in terms of how to make this special type of SDP problem more scalable. I have actually seen some work in this area, like people has developed like parallelization techniques using GPUs to make SDPs more scalable and also find some matrix completion specialized